Hello, good morning. Welcome to the second session of Chapter 3 Matrices of Plus 2 Mathematics. In the last session, we discussed about symmetric matrix, skew symmetric matrix, transpose of the matrix. In this session, we are going to do some results related with symmetric and skew symmetric matrix and some problems based on the theory. Let's recall theorem 1, which we did in the last session. Theorem 1 states that for any square matrix with real number entries, A plus A transpose is symmetric and A minus A transpose is skew symmetric. We've already proved this theorem in the last session using the properties of the transpose. In this session, we'll prove this theorem using a problem. For a matrix A, 1, 5, minus 1, 2, verify that A plus A transpose is a symmetric matrix and A minus A transpose is a skew symmetric matrix. Whenever we want to show any matrix is a symmetric matrix or skew symmetric matrix, we have to find its transpose. If we get back the same matrix, we say that it is symmetric. If that matrix is accompanied by a negative sign, we say that skew symmetric. So let's find A transpose first. A is equal to the matrix 1, 5, minus 1, 2 of order 2 by 2. So when we take the transpose, we can see that the first row 1, 5 becomes the first column. The second row minus 1, 2 becomes the second column. Now we'll find A plus A transpose. For our convenience sake, let's take it as P. So A plus A transpose we find by adding the two matrices. So 1 plus 1 is equal to 2, 5 minus 1 we get 4, minus 1 plus 5 will give you 4, 2 plus 2 is 4. Now to show that it is symmetric, we have to show P transpose is equal to P. So let's take the transpose of P. You can see that you get back the same matrix. Therefore, we can conclude A plus A transpose is a symmetric matrix since P transpose is equal to P. The next question is we are asked to show that A minus A transpose is skew symmetric. So let us find A minus A transpose. So subtracting those two matrices with the corresponding positions, we get 1 minus 1 is 0, 5 minus of minus 1 should be taken, 6. Second row, minus 1 minus 5 is minus 6, 2 minus 2 is 0. Now at a glance you can see that the entries above and below the main diagonal they differ by a sign. Therefore, taking its transpose, Q transpose is equal to the first row 0, 6 becomes the first column. The second row minus 6, 0 becomes the second column. Taking the minus sign out, what do we get? 0. Minus 6 now will become plus 6. 6 becomes minus 6, 0, which is Q itself. So you have proved that Q transpose is equal to minus Q, which means A minus A transpose is a skew symmetric matrix. So we have proved that for any square matrix A plus A transpose is symmetric and A minus A transpose is skew symmetric. Based on this theorem, we'll prove the next theorem, which is an important result. It states that any square matrix can be expressed as the sum of a symmetric and a square symmetric matrix, skew symmetric matrix. Any square matrix can be expressed as a sum of symmetric and a skew symmetric matrix. Just now we have proved in the result that A plus A transpose is symmetric and A minus A transpose is skew symmetric. From theorem 1, we know that A plus A transpose is symmetric and A minus A transpose is skew symmetric matrix. Now the theorem is to show the sum of the symmetric and skew symmetric matrix is the given matrix itself. So when you take A plus A transpose and A minus A transpose, when we add, what happens? Plus A transpose and minus A transpose gets cancelled, but we are getting 2A. So in order to get A, we have to divide by 2. Therefore, we can divide both A plus A transpose and A minus A transpose by 2. Implies that half of A plus A transpose is also symmetric. Multiplying a symmetric matrix by a scalar will not affect the symmetric property. So you can conclude that half of A plus A transpose is also symmetric and half of A minus A transpose is skew symmetric. Therefore, adding these two, half of A plus A transpose plus half of A minus A transpose, when we expand the bracket, you can see that half A transpose minus half A transpose gets cancelled and you are left out with half A plus half A, that is nothing but A. Hence, we have proved that any square matrix can be expressed as the sum of symmetric and a skew symmetric matrix. Now we will do a problem based on this result. First we will consider a matrix of order 2 by 2. Express the matrix A 3, 5, 1, minus 1 as the sum of symmetric and skew symmetric matrix. So the result says you are supposed to show A is equal to half of A plus A transpose plus half of A minus A transpose. So first we have to find half of A plus A transpose. So for our convenience sake, let's take it as P. So let P is equal to half of A plus A transpose. That is half of A matrix plus A transpose. So when we take the transpose of the A matrix, the first row 3, 5 becomes the first column and the second row 1 minus 1 becomes the second column. So adding these two matrices, what do we get? 3 plus 3 is 6, 5 plus 1 is 6, 1 plus 5 6, minus 1 is minus 2. Now dividing by 2, we get 3, 3, 3 minus 1. At a glance, you can say that the entries above and below the main diagonal are same, which means when we take the transpose of P, we get back P itself. Therefore, we can conclude P is a symmetric matrix since P transpose is equal to P. Now we have to find half of A minus A transpose. So let's take it as Q. Q is equal to half of A minus A transpose. So the matrix A minus A transpose. Subtracting, what do we get? 3 minus 3 is 0, 5 minus 1 is 4, 1 minus 5 is minus 4, 0 minus 1 minus of minus 1. So it becomes minus 1 plus 1, that is 0. Dividing by 2, what do we get? 0, 4 divided by 2 is 2, minus 4 divided by 2, minus 2, 0, which is nothing but minus Q. Therefore, we can conclude that Q is a skew symmetric matrix since Q transpose is equal to minus Q. Now we have got one symmetric matrix and one skew symmetric matrix. So finally, we have to show that when you add the symmetric and skew symmetric matrix, we should get back the given matrix. So let's add both the matrices. Therefore, P plus Q will give you P matrix plus Q matrix. Adding, we get 3 plus 0, 3 plus 2, 5, 3 minus 2, 1, minus 1 plus 0 minus 1, which is nothing but the given matrix A. So we have proved that the matrix A of order 2 by 2 in this case is expressed as the sum of symmetric and skew symmetric matrix. Now we'll do a problem taking a matrix of order 3 by 3. So the question, express the matrix A as 6 minus 2, 2, minus 2, 3, minus 1, 2, minus 1, 3 as the sum of symmetric and skew symmetric matrix. Again, recollect the result. You're asked to express a matrix as a sum of symmetric and skew symmetric matrix. That is, you're supposed to write, you have to get A as half of A plus A transpose plus half of A minus A transpose. So let's start with half of A plus A transpose. So let us take P as half of A plus A transpose as we did earlier. Half of the given matrix A plus the transpose of the given matrix. The first row becomes first column, second row becomes second column, third row becomes third column. Moreover, we can see that the matrix A, the entries above and below the main diagonal are same, which means when we take the transpose of such a matrix, we get back the same matrix. That's why you see the same matrix here. So adding both, what do we get? Half of 6 plus 6, 12, minus 2, minus 2, minus 4, 2 plus 2, 4. Second row, minus 2 gives you minus 4, 3 plus 3, 6, minus 1, minus 2. Third row, 2 plus 2, 4, minus 1, minus 2, 3 plus 3, 6. Now dividing by 2, we get 6, minus 2, 2, minus 2, 3, minus 1, 2, minus 1, 3. Again you can see that the entries above and below the main diagonal are the same. So we can conclude P is a symmetric matrix since P transpose is equal to P. Now we have to find half of A minus A transpose. Let us take it as Q, and we have to show that it is a skew symmetric matrix. So Q is equal to half of A minus A transpose. Half of A minus the transpose of the matrix. So when you subtract 6 minus 6 is 0, minus 2 minus of minus 2, that is plus 2 is 0, 2 minus 2 is 0. The second row, minus 2 minus of minus 2 gives minus 2 plus 2, that is also 0. 3 minus 3 0, minus 1 minus of minus 1, that is minus 1 plus 1, that gives 0. 2 minus 2 0, minus 1 minus of minus 1 0, and finally 3 minus 3 0. So dividing this by 2 also gives us a 0 matrix, and we know that a 0 matrix is a matrix which is both symmetric and skew symmetric. Therefore we can conclude Q is a skew symmetric matrix since Q transpose is equal to minus Q. So now we have got a symmetric matrix and a skew symmetric matrix, and we have to show sum of the symmetric and skew symmetric matrix gives the matrix A. So adding P plus Q, we are adding both the matrices, we get back the same matrix A. Thus we have proved matrix A can be expressed as a sum of symmetric and skew symmetric matrix. For any square matrix, A can be expressed as a sum of symmetric and skew symmetric matrix. In the last session, we discussed about the properties of transpose. Few properties are A transpose is A plus B the whole transpose is A transpose plus B transpose, A minus B the whole transpose is A transpose minus B transpose, AB the whole transpose, B transpose A transpose, which is called as reversal law, and KA the whole transpose is K into A transpose. Let's verify those properties through problems. So problem 1 here, if A transpose is equal to the matrix of order 3 by 2, 3 rows and 2 columns, 3, 4, minus 1, 2, 0, 1. And B is a matrix of order 2 by 3, minus 1, 2, 1, 1, 2, 3. You are asked to find A, the first question. Second question, you are asked to verify A plus B the whole transpose is equal to A transpose plus B transpose. Okay, let's see to the first question. In the question, you are given A transpose and you are asked to find A. Now, connecting to the property of the transpose, when we take the transpose of A transpose, we get A. Therefore, A is equal to the transpose of A transpose. So, the first row becomes first column 3, 4. Second row minus 1, 2 becomes the second column. And the third row 0, 1 becomes the third column here. So, the transpose of A transpose is A itself. Now, let's verify property 2. That is, we have to prove A plus B the whole transpose is equal to A transpose plus B transpose. Let's take the LHS first. In order to find A plus B the whole transpose, we have to find A plus B first. So, let's start. Take the LHS, add the two matrices. So, adding, this is our A. So, A plus B, 3 minus 1 will give you 2, minus 1 plus 2 is 1, 0 plus 1 is 1, 4 plus 1, 5, 2 plus 2, 4, 1 plus 3, 4. Now, taking the transpose, we get A plus B the whole transposes. The first row 2, 1, 1 becomes the first column. The second row 5, 4, 4 becomes the second column. So, this is our LHS. Now, we have to find the RHS. So, we have to find A transpose plus B transpose. So, A transpose is given in the question. By taking the transpose of B, we get the B transpose. So, adding both, what do we get? 3 minus 1 is 2, 4 plus 1, 5, minus 1 plus 2, 1, 2 plus 2, 4, 0 plus 1, 1, 1 plus 3, 4. This is our RHS, and the LHS, note there, what we got is the same matrix. So, comparing both LHS and RHS, we can see that A plus B the whole transpose is equal to A transpose plus B transpose. Hence, one of the property is verified. Now, let's go to the next question. To verify AB the whole transpose is equal to B transpose A transpose, you are coming in the reverse order. That is why it's called as reversal law. So, let's take the LHS. In order to find AB the whole transpose, we have to find AB first. So, A is given to be a column matrix, B is given to be a row matrix. Let's find A into B. By the rule of the multiplication, we can see that A is a matrix of order 3 by 1 and B is a matrix of order 1 by 3. So, we know that the resulting matrix will be of the order 3 by 3, which means it will have 9 elements. So, let's see. So, 1 into minus 1, 1 into 2, 2, 1 into 1, 1. Coming to the second row, minus 4 into minus 1, it's 4, minus 4 into 2, minus 8, minus 4 into 1, minus 4. Third row, 3 into minus 1, minus 3, 3 into 2, 6, 3 into 1, 3. So, we have multiplied the matrices A and B. Now, let's take the transpose. The first row will become the first column, the second row becomes second column, and the third row becomes third column. So, the LHS we have found out. AB the whole transpose, we got it now. Now, we are going to find the RHS. First, we will find B transpose, which will become the column matrix. A transpose, which now will become the row matrix. We will multiply both the matrices. So, B transpose is the column matrix minus 1, 2, 1. A transpose row matrix 1 minus 4 3. So it should be taken in the reverse order. So B transpose A transpose is equal to, as usual, this is the matrix of order 3 by 1. This is the matrix of order 1 by 3. So when you multiply, you get a matrix of order 3 by 3, which will have 9 entries. So minus 1 into 1, minus 1, minus 1 into minus 4, 4, minus 1 into 3, minus 3. Second row, 2 into 1, 2, 2 into minus 4, minus 8, 2 into 3, 6. The third row, 1 into 1, 1, 1 into minus 4, minus 4, 1 into 3, 3. So the LHS is written over there and the RHS is here. So comparing both the answers, we see that LHS is equal to RHS. Therefore, we can say that AB the whole transpose is B transpose A transpose. Hence, we have verified the law here. Next problem. If A and B are symmetric matrices, prove that AB minus BA is a skew symmetric matrix. If A and B are symmetric matrices, recollect the definition of the symmetric matrix. When I say A is a symmetric matrix, we have A transpose is equal to A. When B is a symmetric matrix, we have B transpose is equal to B. You are asked to show AB minus BA is a skew symmetric matrix. So, whenever we want to show any matrix is a skew symmetric matrix, we have to take its transpose and show that it is accompanied by a negative sign. So, let us take AB minus BA the whole transpose. So, AB minus BA the whole transpose. By the property of the transpose, we can write A minus B the whole transpose as A transpose minus B transpose. Therefore, this is equal to AB the whole transpose minus BA the whole transpose. AB minus BA the whole transpose is equal to AB the whole transpose minus BA the whole transpose. Just now we have proved the reversal law. What is AB transpose? It is nothing but B transpose into A transpose minus BA the whole transpose coming in the reverse order, A transpose into B transpose. Since A and B are symmetric matrices, we are going to replace A transpose as A and B transpose as B. So, B transpose becomes B, A transpose is replaced by A minus A transpose is replaced by A and B transpose is replaced by B. Now, taking the minus sign out, we get minus of AB minus BA. That is, we have proved AB minus BA the whole transpose is equal to minus of AB minus BA. Therefore, we can conclude that AB minus BA is a skew symmetric matrix. Next problem. If A is equal to the matrix 3 minus 4, 1 minus 1, then you are asked to prove that A raised to n is equal to the matrix 1 plus 2n minus 4n, n 1 minus 2n, where n is a positive integer. So, when you are given A square, we multiply as A into A. When you are given A cube, we multiply A into A into A. Here, you are asked to prove that for any n, that A raised to n is equal to the given matrix. So, whenever you want to generalize any result, we use one principle which you have studied in the +1. That is called as principle of mathematical induction. It states, it has got 3 steps. The first step is what? We put n is equal to 1 and we show that P of 1 is true. The second step, we assume P of k is true by putting n as k. In the third step, we take n as k plus 1 and we prove P of k plus 1 is true. So that is what the principle of mathematical induction says. So let's start. Let's take P of n to be the given statement. A raised to n is equal to matrix 1 plus 2n minus 4n, n 1 minus 2n. Let's put n is equal to 1. What happens? A raised to 1 is equal to, wherever n is going to come, it will be replaced by 1. So 1 plus 2 into 1, minus 4 into 1, 1, 1 minus 2 into 1. Simplifying, we get 3 minus 4, 1 minus 1, which is nothing but the given matrix A. So we have proved when n is equal to 1, A raised to 1 is A itself, which implies P of 1 is true. Now we'll go to the second step. Assume P of k is true. That is, you're going to put n as k in the given problem and you're going to rewrite the whole problem by replacing n by k. So assume that P of k is true. That is, A raised to k is equal to 1 plus 2k minus 4k, k 1 minus 2k. You're rewriting the whole problem by replacing n as k. Now based on this assumption, we are going to prove P of k plus 1 is true. That is, when n is equal to k plus 1, we get A raised to k plus 1 equal to 1 plus twice of k plus 1 minus 4 into k plus 1, k plus 1, 1 minus 2 of k plus 1. So let's start with the LHS. So A raised to k plus 1, we can write it as A into A raised to k. So replacing A as 3 minus 4, 1 minus 1, and A raised to k, the assumption matrix. Now multiplying both the matrices, we get the first row, first column. So 3 into 1 plus 2k minus 4k. Next, first row, second column, 3 into minus 4k plus minus 4 into 1 minus 2k. Second row, first column, so 1 into 1 plus 2k minus k. Second row, second column, 1 into minus 4k minus 1 into 1 minus 2k. That is the multiplication rule. Now simplifying, 3 into 1 plus 3 into 2k, 6k minus 4k. Coming to this, 3 into minus 4k is minus 12k, minus 4 into 1 is minus 4, minus 4 into minus 2k will give you plus 8k. In this, 1 plus 2k minus k will give 1 plus k, minus 4k, minus 1 into 1 gives minus 1, minus into minus plus 1 into 2k, 2k. So simplifying, we get 3 plus 2k minus 4 minus 4k, 1 plus k minus 4k plus 2k will give you minus 2k minus 1. This we can rearrange it as 1 plus 2 into k plus 1 minus 4 of k plus 1, 1 plus k minus 1 minus 2k plus 1. You can see that they are equal. So rearranging in this way, we have proved that that is equal to our RHS. Hence we have proved P of k plus 1 is true. Therefore, P of n is true for all n belonging to n. With this, we come to the end of this session. Thank you.